Hey, it's Dr. J. I'm back with part 2 today of rational functions. So today we're going to focus on functions. Remember, a rational function is a polynomial divided by a polynomial. Yeah, it's the ratio of two polynomials. So P and Q are polys. In my first edition of this video, we've used linear polynomials or constant polynomials, so much simpler than today. Today we're going to focus where the degree is 2. I don't know. Well, it took me so long to get that word out. I was thinking maybe they're not all going to be degree 2, but we're going to focus on polynomials of degree 2. So, for example, quadratics. Let's just get right into it. I guess I'll call this one example 1. I'm going to ask the same types of questions that I asked yesterday, or I don't know if it was yesterday, but whenever you watch the first part of this video in part 1. So I'll ask about things like intercepts and asymptotes and such and such. So here we go. So this is what I meant. Today we're going to focus on degree 2 polynomials, or degree 2 quotients of degree 2. So same types of questions I want to ask. I want to find the intercepts and the asymptotes. Let's go ahead and do the intercepts first. By far the easiest intercept is the y-intercept. You just simply plug in 0 for x. I'm going to show all of this work one time, and then in the rest of these examples, I hope that we can generalize this so that we don't have to do this enormous calculation, which is not really very enormous. It just takes a lot of writing. So I'm going to do this once. I'll show you how to do it, and then in the future we'll generalize this to make it a lot easier for you. So when you plug in 0 into a polynomial, we've seen this before, it kills, all the terms become 0, except for the last terms, the constant terms. So you get 4 over negative 8, which is negative 1/2. And then make sure that you write it correctly. So the y-intercept is 0, comma, negative 1/2. All right, now the x-intercepts are a little tougher, although they're not much tougher. You just have to remember the technique. You're going to set p of x equal to 0. Remember, p of x is also known as the numerator of the rational function. All right, we'll set that sucker equal to 0. Now, hopefully you won't need the quadratic formula. Although if you get desperate, or if this polynomial is difficult to factor, or you just have no, clue on how to break it up, then go ahead and use the quadratic formula. I'm going to try to avoid that at all costs. So we have 3x and x. All right, I'm just guessing. 3x times 1x is 3x squared. I'm going to ignore the middle term while I'm guessing, and I'm going to look at the last term. Let's try 4 and 1. Notice how I don't put the signs right away. I can always adjust those later. My guess is that they're both going to be negative. It's a pretty good guess, because if the middle term is negative and the last term, constant term, is positive, they're both going to be negative. But you'll notice now that the middle term is not going to come out to be 13. I know this is a little bit elementary for your level, but it never hurts to review it. So when we're checking the middle term to see if it comes out to be negative 13, or at least 13. We can make it negative in a minute. So 3 times 1 is 3, and 3x times 1 is 3x, and 4 times 1x is 4x, and there's no way that's going to ever be 13, right? 3x and 4x, it could make 7 x, yeah, or it could make 1x or negative 1x, some combination of 3 and 4, but it's never going to be 13. So I'm going to change my guess. I'm going to guess the last term to be 4 and this middle term to be 1. And then now you can see if I make them both negative and I check, I get 3 times negative 4, 3x times negative 4, which is negative 12x, and then negative 1 times x is negative 1x, and that clearly makes 13x. If you're good at factoring, if you've done it in your elementary or intermediate algebra courses or high school algebra or whatever you had before college algebra, or before, this is sort of leaning towards college algebra, pre-calculus level here. If you're good at factoring, that step will be a lot faster. Okay, and then you're going to set these both equal to 0. So 3x minus 1 equals 0. Again, I'm showing the work just to kind of get the ball rolling, but I think you can probably do this all mentally. Divide by 3 and you get 1/3. All right, and then the other one, I sincerely hope you can do this one mentally. If you have x minus 4 is equal to 0, you're clearly going to get x equals 4. And then a common mistake is putting these two numbers together. They are intercepts. They're separate intercepts. So when I list out my answers, it's 1/3, comma 0, comma 4, comma 0. So I separate them with a comma. Whenever possible, I use fractions instead of decimals. As you could probably imagine, those decimals, this would be 0.33333. And it's probably not very useful to write it that way. All right, so that's the intercepts. Quick review of the intercepts. That should be pretty straightforward. Now let's go ahead and find the asymptotes. Now I'm going to do this one more time from the last video. The horizontal asymptote, we look for a tendency as x gets very large. Okay. I'm really pressed for space here, so let me just see if I can move up here a little bit. So for the horizontal asymptote, the HA, we let x get very, very large. Let x approach infinity. All right. And again, I used a big number like 1,000, or I think the very first time I did it was with 1,000,000, but it's a lot of zeros, so I'm just going to use 1,000. So look what happens when you plug in 1,000 here, right? And I'm only going to do this once, and then we're going to have a nicer way to do it. So f of 1,000, right? We're asking ourselves, what happens as x gets very, very large, right? What's the tendency? Well, 3 times 1,000 squared minus 13 times 1,000 plus 4. And then another 3 times 1,000 squared plus 10 times 1,000 minus 8. Yeah? Let's see if I can get that into the camera range there. All right, so we're down here at the bottom of the screen here. All right, so what is that? All right, well, 1,000 squared is 1,000,000, so that's going to be 3 million. Yeah? 1,000 squared, 1,000 times 1,000 is 1,000,000. That's what 1,000,000 really is 1,000 thousands, yeah? And then it's going to be minus 13,000, yeah? 13,000, and then plus 4, yeah? And the bottom, similarly, that'll be 3 million plus 10,000 minus 8. Well, again, as I mentioned before, these smaller numbers, 13,000 and plus 4 and 10,000 and minus 8, they're insignificant compared to the leading term. So the leading term is still 3 million divided by 3 million. Yeah, that's its tendency is to dominate the value with the leading term. The leading term is one of the reasons why we call it the leader, right? So it just basically makes these smaller numbers insignificant, and this is approximately 1. Yeah, 3 million divided by 3 million. So the horizontal asymptote is y equals 1. It'd be nice if we just had a recipe for the y-intercept. I mean, for the horizontal asymptote. We do have a recipe for the y-intercept. I did it over here, but so for the horizontal asymptote, there is a recipe. Or you could call it a formula, or you could call it a generalization. Yeah. And there's three possibilities. If the degree of P is equal to the degree of Q, you remember P is the numerator and Q is the denominator, then the HA is Y equals A over B, where A and B are the leading coefficients. Coefs of P and Q, respectively. All right, so A is the leading coefficient of P, that's A, and B is the leading coefficient of Q. So that's only if the degree of the numerator and the degree of the denominator are the same. All right. I'm going to need to write this equation over here so I don't lose it. 3x squared minus 13x plus 4. I have to erase this temporarily. 3x squared plus 10x, where I wish I had a larger board. We're going to need a bigger board. All right. So number 2, if the degree of the numerator is less than the degree of the denominator, so for example, maybe the numerator is linear or constant, and the denominator is larger than linear, so quadratic or higher. All right, so if the numerator is smaller, well, we saw this in part 1. If the numerator is smaller than the denominator, when you do this tendency, when you plug in a large number for x, the denominator gets very, very large, yeah, and the numerator is relatively small. So the HA is very simple. It's the x-axis, yeah, y equals 0. It's the x-axis. And the third case is if the degree of the numerator is larger than the degree of the denominator, then the HA does not exist. It's DNE. All right, and so we can see here that the HA is y equals 1 because it's case number 1. The numerator divided by the denominator, the numerator and the denominator have the same degree. They're both second degree, see? I don't know if you can see that 2 there. They're both quadratic. So we look at the leading coefficient. We take their ratio, 3 divided by 3, and we get 1. So that's our HA. All right, this is going to make finding the horizontal asymptotes for the rest of these examples a lot quicker. Okay. We no longer have to plug in large numbers for x. Although I will mention, if you are ever stuck or you can't remember the 3 different possibilities, then you can plug in a large number for x and calculate what the asymptote is that way. Okay. Finally, the VA, the vertical asymptote, we're going to set Q of x to equal 0. All right, so Q of x equal to 0. So that's the denominator. 3x squared plus 10x minus 8 equals 0, like that. And again, try to factor it before resorting to any kind of quadratic formula or anything like that. How about 4 and 2? 4 times 2 make 8. If I do a positive 4 and a negative 2, double check the middle term will come out to be 10. So 3x and 4 is 12x. And then minus 2x. So that gives you 10x again. A quick check of the outer and the inner terms can verify that this middle term checks out. Okay, so my asymptotes are 3x minus 2 equals 0. Again, I'm going to skip the steps. You're pretty advanced at this point, so that'll be 2/3. We're pretty far along in the course, so that'll be 2/3. And then x plus 4 would be -4. All right. Now, these are asymptotes, so we do not write them as coordinates. We write them as lines. So the VAs, there's actually 2 of them, are x equals 2/3 and x equals comma x equals -4. Those are our VAs. And so there's our summary. We have our y-intercept, we have 2 x-intercepts, we have a horizontal asymptote, and we have a vertical asymptote. Which means we have a pretty good idea of what the graph looks like. I did bring some graphing boards today, so we might see these in more detail. But since this is only my first example, we've got a lot more to do today, so we should get on with it. All right. Okay, so that pretty much wraps that one up. You might want to have this formula handy. We'll use it for the rest of the examples today. Example 2, same type of question. So we got 3x squared minus 7x minus 6 and 2x squared minus 3x minus 20. All right, same concept. Find the intercepts. So let's do the y-intercept first. Plug in 0. And again, I don't have to show all the math anymore, right? 0, 0, 0, 0. These are all going to become 0. So you're just going to get the constant terms. -6 divided by -20. Reduce that if possible. 6 is 2 times 3, and 20 is 2 times 10. So that will reduce to 3/10. All right. And again, write it as a pair. 0, 3/10. That's your y-intercept. Okay. X-intercept. Set the numerator equal to 0. A little comment. In part 1 of the video, I was asking for the domain. I'm not sure if I'm going to ask for that today. Maybe. I think so. I peeked ahead. If I'm asking for the domain, then we say not equal to 0. All right. When we ask for the, when we're asking for the domain, we're looking at the denominator. Yeah. For the x-intercepts, there's actually more than one. We set the numerator equal to 0. So I want to point that out. There's 2 different parts to the function. So the denominator would tell us the domain or the vertical asymptotes, and the numerator would tell us the intercepts, the x-intercepts. And again, try to avoid using the quadratic formula unless you absolutely have to. Let's try 3 and 2. 3 times 2 makes 6. And now I'm hoping I can get a 7 out of the middle. Notice I don't put the signs quite yet. I can always adjust those later. So 3 times 3 is 9. And then 2 times 1 is 2. So I can make a 7 out of that if I do a positive 2 and a -9. So 3 times -3 would be -9. Check. That's going to make -7. All right. And then you get your intercepts pretty quickly. You're going to get 3x plus 2 is equal to 0. So x is equal to -2/3. And then x minus 3 is equal to 0, so x is equal to 3. And then again, write these as pairs, -2/3, 0, 3, 0. So those are your x-intercepts. All right. Horizontal asymptote. Again, the degree of the numerator and the degree of the denominator are the same. They're both second degree. So the horizontal asymptote is y equals 3/2. It's a over b. All right, so there's your A is 3, and your B is 2, so it's A over B. Remember, asymptote is an equation. All right, and then this was my comment about the vertical asymptotes, which might have been a little premature, but now we're there. For the vertical asymptotes, you set the denominator equal to 0 and solve it. And again, if I was asking for domain, domain is the same technique as the vertical asymptote, but with domain, you say it's not equal to 0, right? Because you're saying, well, x can be any number except whatever causes the denominator to be 0. So again, it's just a different take on the same concept. All right, give this a factorization. 2x times x. That's a good guess. Now I got to guess two numbers to make 20. So I could do 5 and 4 or 2 and 10. I usually go with the more moderate number in the middle, 5 and 4. If that doesn't work, maybe I would try 2 and 10. And then my worst case guess would be 1 and 20. 1 times 20 is 20. I think 5 and 4 will work. All right, remember now I'm trying to get -3. So I'm going to do a -4. That makes it 8, -8. 2 times -4 is -8. And then I go to the middle and I make that positive. If the outer is -8, and then the inner is +5, check, that comes out to be -3. So I get two vertical asymptotes. I get one of them is -5/2. I got to move the 5 over, make it negative. And then the other one is 4. X equals 4. So those are your two vertical asymptotes. So summarizing everything, you've got two vertical asymptotes, you've got one horizontal asymptote, and then you've got these intercepts. Just for fun, we could draw a graph. Oh no. Not too detailed, but yeah, let's go this way. Let's assume that each block represents 1. Actually, I regret that. Let's use the larger board. You'll be able to see a little bit better. All right, so just for fun, I like to see what this thing looks like. So again, I'm going to exaggerate my scale here. We're going to do 1, 2, 3, and -1. Sometimes I think I know what I want to do, and then I change my mind. So we'll do 1, 2, 3. We'll do 1, 2, -1, -2. All right. I like to put my asymptotes down first. So my horizontal asymptote is 3/2, which is the same as 1.5. All right, so in my head, I'm thinking 1.5. So it's right here in between 1 and 2. I have two vertical asymptotes. I got one over here at 4. So right here. And one at -2.5, yeah? So I see 5/2, but I think 2.5, -2.5, so right about here. All right, so that's sort of my framework for this graph. All right, and now I put down my intercepts, so it looks like I've got an x-intercept at 3, and another one at -2/3, which I'm just going to approximate right about there, a little closer to -1. And then I got my y-intercept as 3/10. Now 3/10 is not very easy to graph, so I'm just going to make a dot very close to 0. And so this is kind of what it looks like. Okay. And then it has these wings over here, which I'll get into more detail. I wasn't really intending on graphing this one, but since I had already talked so much about it, I figured I might as well show you what it looks like. So that's sort of rough sketch. I'm not being very detailed about all the coordinates, but I at least have the important information, the asymptotes, the intercepts. Probably wouldn't hurt to, maybe plug in a number like 5 and just verify that you do in fact get a dot up in that quadrant or in that region. Similarly over here, you could plug in -3. I'm not going to do it, but you could verify that if you plugged in -3, you would get a number larger than 1. Excuse me, larger than 1.5. So closer to 2. Again, I just estimated that. I don't know what it exactly is. I actually erased the original problem a long time ago, so it's gone. Okay. There is some graphing later on, or at least some questions about graphing. So we'll keep this on hold and come back to it if necessary. Some dishes going on in the background. So, all right, example 3. These are slow going, so hope you don't have anywhere to be right now. All right, so this time we've got a linear 5x minus 4 divided by a quadratic 4x squared minus 25x plus 25. So let's go ahead and find everything, including domain. Intercepts, so find the domain, the intercepts, and the asymptotes. All right. So again, I mentioned domain in part 1 of the video. The domain is related to the vertical asymptote. So you look at the denominator. Now when you're doing domain, you set it not equal to 0. It's the only difference. Which is kind of like a buy one, get one free. So if I do the domain now, I do it at the beginning of the problem, then when I get to the section, the problem on asymptotes, I already have at least one of the asymptotes. Or the vertical asymptotes. All right. Again, factoring is key here. So we got, say, 4 and 1, and 5 and 5. Yeah. And I just guessed, just sort of the moderate guess. If that didn't work, I might have tried 2 and 2 instead of 4 and 1. I think this works, though, if I do my signs right. So negative and a negative. There is a general pattern. If the last term is positive and the middle term is negative, then these must both be negative. And then just double check, eyeball it. 4 times 5 is 20, or negative 20. It's a negative 5. And then negative 5 and 1 is negative 5. And so that does, in fact, make negative 25. So then I get x is not equal to 5/4 for this one, and x is not equal to 5. So notice I also get the VAs. You just change this to equal to. Yeah, so the only difference between vertical asymptotes and domain is the vertical asymptotes are equal to and the domain is not equal to. I also write domain using interval notation. So negative infinity to 5/4, union 5/4 to 5, union 5 to infinity. That's the standard interval notation for domain. The other notation is you could use the fancy set braces. We've done that in the past as well. It really depends. On paper, I like to use the set braces, what I call fancy pants. But on a computer, when you're typing the answer, this is much more user-friendly for typing. So we got the domain. We've got 2 asymptotes. Let's go ahead and do the horizontal asymptote while we have it here. Now this time, the degree of the numerator is smaller than the degree So the degree of P is smaller than the degree of Q. All right, degree of the denominator is 2. Degree of the numerator is 1, so the numerator is smaller. And so the HA is the x-axis, y equals 0. So it has a dotted line right on the x-axis that it has a tendency to approach that value. An interesting fun fact about graphs, which we'll get to later, but I might as well mention it now. Vertical asymptotes are never to be crossed. So it's a thou shalt not ever equal these numbers. You cannot ever touch those numbers, right? It's like a forbidden number. It's an excluded number. So these numbers are never touched on the graph. However, horizontal asymptotes are what we call a tendency. It has a tendency to get close to that number. It might actually touch it. Right? It could touch it. It's not as strict as a vertical asymptote. Okay. So I've got the asymptotes. I've got the domain. The only thing left to do is the intercepts. Again, as before, the y-intercept is the easiest. You just plug in 0, and it kills all the x's. All the x's annihilate. It becomes 0, and you just get -4 over 25, which cannot be reduced. So I'm just going to write my answer as a fraction, -4/25. It's very, very small, very, very close to 0. Okay. And then the x-intercept, notice there's only 1. So for the x-intercept, we're going to set the numerator equal to 0 and solve it. You're going to get 4/5. So your answer is 4/5, 0. All right, and that summarizes it. We have the x-intercept. There's only 1. We got the y-intercept. We got a horizontal asymptote, and we have 2 vertical asymptotes. I'm not going to bother graphing this one. The numbers are not very friendly numbers. So. Okay, moving right along. Example 4. Seem to be getting this 3x squared a lot. Not a lot of variety in these problems. I've tried to make variety, and it just makes the problems a nightmare. So I just like keep them nice and simple. Turns out you don't have to make a problem very hard in order for it to be multifaceted. There's a lot of steps to this, so keeping the problem simple helps illustrate the concept without overburdening us. Believe me, I've tried to make up crazy examples, and it's just not worth the trouble. So I can use kind of the same format over and over again, and you'll see what happens here. Basically the same question. Let's do everything. Let's do the domain. Let's do the intercept. So find the domain, the intercepts, same question, and asymptotes. All right, let's get right to it. Domain, you take the denominator and you set it not equal to 0. So that means x is not equal to 1/4. So the domain, say dom, -infinity to 1/4, union 1/4 to infinity. It only has one union because there's only one exclusion. If there's 2 exclusions, then you get 2 unions. The number of disjoint sets is one more than the number of exclusions. So there are 2 disjoint sets because there's one excluded number. Remember, excluded numbers use open parentheses because it's not touching that number. You also get the VA for free. Just tell me it's equal to that number. X is equal to 1/4. The HA, all right, so this time the degree of the numerator is 2 and the degree of the denominator is 1. So the degree of P is greater than the degree of Q. And so that means the HA does not exist. Yeah. One way to think about that, I mean, you could just memorize the formula because I told you, but remember, hopefully you remember at the beginning of this lecture and in my previous lecture, to find the HA, I didn't have that rule of three. We were doing it old-fashioned way by plugging in number, like 1,000 or 1,000,000 or something, right? Well, think about that. If you plugged in a big number here, yeah, the numerator is squared, so the numerator is going to get huge, right? If you plugged in 1,000,000, that would be 1,000,000 squared, right? It'd be huge. I don't even know what 1,000,000 squared is. It has 12 zeros. I guess that's a quadrillion? I don't know. You have to look that one up. Google that one. All right, it'd be a 3 followed by 12 zeros. All right, that's big. Yeah, the denominator would only be 4 million. Right, and so even though the denominator is still pretty big, 4 million, the numerator is enormous. Right, I like to think of it as swallowing up the value it's in the denominator. So the numerator dominates the value, and that just doesn't have a tendency to approach any particular number. Although it might approach something, it's just not a number, and we'll get into that later. Okay, so there is no horizontal asymptote. Just put DNE, does not exist. Okay, let's do the y-intercept. Of course, that's the easier of the two intercepts. Just plug in 0. It kills all the x's, and you get 8 over -1, which is -8. So your y-intercept is 0, -8. All right. And then the x-intercept, or intercepts. Last time there was only 1, but this time there'll be 2. You can kind of tell by the power. Second degree will have typically 2 solutions. Typically. There might be exceptions, but for the most part, quadratic equations separate into 2 factors. All right. Again, I'm sliding my thing down, but I'm taking the numerator, I'm bringing it down here, and I'm giving myself some space to work. Well, you're going to be really good at factoring these 3x squareds after this. I think there's several of these. All right, and then we got 8. All right, so I'm guessing 2 numbers that make 8. So I usually go with 4 and 2 if it's 8. And then if that doesn't work, I'll try 8 times 1. But let's try 4 times 2 first. And then I might switch the 4 and the 2 if necessary. Let's try this. Negative, negative, so I get negative 4 times 3 is -12, -12x. And then I got -2x in the middle, and check, that equals -14. One mistake people make with factoring, if you haven't done it in a while, is guessing while looking at that middle number. I find that throws you off, because when you're guessing the numbers here, it might not be apparent while you're guessing that they actually do combine to become that middle number. So I recommend looking at the leading term and guessing, looking at the constant term and guessing, and then just hoping, sometimes I call it guess and hope, that the middle number comes out right. And if it doesn't, that's okay, right? I can always guess again, right? I've had to guess more than once. You're going to get so good at it that you could probably get it on your first guess. I also hope that you're so good at these that you can solve these with mental math. So you're going to get x equals 2/3, right? Remember, you're setting these equal to 0. And you're going to get x equals 4. And then remember to write them correctly. 2/3, comma 0, comma 4, comma 0. And those are your x-intercepts. Okay, so let's talk more about what happens when there's no horizontal asymptote. If there's no HA, then there may be, I'm going to say there is, but it's actually a maybe. a slant asymptote? I mean, I could make up some examples where there is no slant asymptote. I could do that, but I'm not going to. At this point, we're almost done with this lesson. I just want to make sure that you understand that there is going to be a slant asymptote whenever there's no horizontal asymptote. All right. And so whenever the numerator, the P, is greater than the degree of Q, the denominator, sometimes my G's and my Q's look similar, so the degree of Q. Whenever the degree is one more than, but it really means like the degree of the numerator is second degree and the degree of the denominator is first degree. For all practical purposes, that's the type, that's the category that we're dealing with. Although there are more elaborate categories, at this point to introduce them would just be more trouble and more confusing than it's worth. So let's just take into consideration the numerator is going to be second degree and the denominator is going to be first degree. All right. There's what's called a slant asymptote, which it kind of looks like this. Where's my red pen? Now, again, I'm just making this up, but we'll do an actual example in a minute. But this is what a slant asymptote looks like. It's sometimes called an oblique asymptote. Yeah. And so basically what happens is the graph kind of has a tendency to get close to this line as you go towards infinity. So as x goes towards infinity or as x goes towards negative infinity, the graph has a tendency to get closer and closer to this line. So it kind of hugs up against it. We call that a slant or an oblique asymptote. So let's do an example. I kind of already gave it away. So let's do the numerator is an x squared, 4x squared minus 27x, and the denominator is x minus 7. So there is a VA. The VA is pretty straightforward. It's x is equal to 7. Yeah. So there's still a vertical asymptote, but there is no horizontal asymptote. Horizontal is DNE because the numerator is larger than the denominator. So to find the slant, use long division. Remember long division? We learned it in the section on division. The denominator is your divisor. The numerator is the dividend. And then you guess, right? So what times x is 4x squared? You know, I call it guessing, but I think in my video I said there's really only one reasonable guess. It's more like insist that this number is the correct number. So 4x times x is 4x squared, and then 4x times negative 7 is negative 28x. And then remember, change the signs. I like to use a different color, so that reminds me that I did it already. So that becomes negative. These guys cancel. This becomes positive. We add these together or subtract them, whichever is appropriate. In this case, it's negative 27 plus 28, which is 1x. Okay. If there's a number here, bring it down. If not, it's a 0. Sometimes there's a constant number. If there's not a constant number, it's 0. So now your dividend is 1x plus 0. And again, you guess what, or insist, what times this x would equal 1x? Well, clearly 1, yeah? positive 1. Positive 1 times x would be positive 1x. And then positive 1 times negative 7 would be negative 7. You can stop now, actually. I'm going to finish it, but you can stop. You're going to change the signs, kill the leader, and then your remainder, you add these together. In case you haven't done division in a while, so your remainder is 7. Okay. Now, you may ignore the remainder when you're finding the slant asymptote. Your slant is the equation y equals 4x plus 1. So it's a slanted asymptote, y equals 4x plus 1. Now you got to remember to put the y, because the y is not going to show up on its own. It's not going to volunteer itself. Right? This is essentially an equation, y equals 4x plus 1. To give you an idea of what it would look like, so I would go to 1 and put a dot at y equals 1, and then my slope would be up 4 over 1. It'd be a very steep line like this. So this is the line y equals 4x plus 1. That's your slant asymptote. Your vertical asymptote would be at 7. So 1, 2, 3, 4, 5, 6, 7. It's not very easy to see the graph, but it's in there somewhere. Somewhere off the plane, off my little graphing board, these asymptotes will intersect with each other like this. All right. And just a rough idea of what the graph looks like, it would be something like this. And again, I'm just guessing. I know that it goes through 0. Yeah, but I don't know. I'd have to put more thought into what the graph looks like. I mean, I guess I could do it. You want to look at the intercepts? Yeah, I wish I never even said it now. So you'd have 4x minus 27 and then times x. I'm factoring out the top. Set it equal to 0. I get x equals 0 and x equals 27 fourths. So 27 fourths is right about here. It's very close to 7. Yeah, it's like 6 point something. 6.25 or 6.75. Yeah. 4 goes into 27 6 times with a remainder of 3. So it'd be 6 3/4, so 6.7. So there's a dot, and then there's another dot. So yeah. So the graph would look like a little parabola, or not a little parabola, pretty good sized parabola, kind of pinned in there. And then there'd be another little piece of it up here out of the window. It's hard to see because my graphing board's not big enough. So again, I said I wasn't going to put a lot of time into it, but you know me, once I get started, it's hard to shut me up. So all right. So that's how you do slant asymptotes. Maybe let's do one more, because those are kind of new. You've never seen them before. Example 6. I'm not sure if I lost count. We might be up to 7, but let's see. Okay, so we've got a function that is 18x squared plus 18x minus 1 over 3x minus 1. All right, let's do the VA first. The VA, we look at the denominator. X is equal to 1/3. Yeah, set the denominator equal to 0. Horizontal asymptote does not exist because the numerator has a larger degree than the denominator. So to find the slant, we divide. We can ignore the remainder. And we're just going to look at the quotient line here. So again, insist that this is the right number. What times 3x would be 18x squared? Well, there's only one possibility. It's 6x. 6x times 3x squared is, in fact, 18x squared. 6x times -1 is -6x. And then change the signs. Kill the leader. Add or subtract as appropriate. So that'll be 24x. This time the constant term is -1. Again, insist. Right? What times 3x would be 24x? Well, 8. Positive 8. Positive 8 times 3x would be 24x. Positive 8 times -1 would be -8. Change the sign. Kill the leader. Add or subtract as appropriate. So that would be adding, or subtracting 1, or adding -1 plus 8, remainder 7. Ignore the remainder. Now, if you're still catching up on some of the division assignments, don't ignore the remainder. If it's a pure division problem, I want the remainder as well. This is not really a division problem. I'm using division as a tool. The goal here is to find the slant asymptote. So the slant asymptote is y equals 6x plus 8. All right, and I'm not going to bother drawing this one. This one's pretty messy. In your mind, you can imagine a very steep line. The slope is 6, has a pretty steep slant, crossing the y-intercept at 8, the y-axis at 8. And then it would have a vertical asymptote at 1/3. And it would look very similar to the one that we just did. Different values, though, of course. OK, so the next thing that could happen next, we consider what are we called removable discontinuities. Removable discontinuities. That's whenever P and Q have a common factor. That hasn't happened yet, but it's going to. Setting the stage for this to happen. If you have something like this, x squared plus 9x plus 8 over x squared plus 12x plus 32. So P is the numerator, Q is the denominator. And if they have a common factor, which I kind of gave it away, x plus 8, x plus 1, that's the numerator. And the denominator is x plus 8, x plus 4. This is called a removable discontinuity. Right. And it occurs when this value is equal to 0. Set the factor equal to 0. Now, since they're both the same, it doesn't matter which one you set to 0. They will be the same factor. So just pick one of them and set it equal to 0. They're both, you don't have to do it twice. And so x is equal to -8. Technically, x is not equal to -8 since this value is excluded from the domain. All right. So technically, we say this is not equal to -8. And I'm saying that as a technicality That's pretty blurry, because I want you to actually give me the number -8. I don't really want you to say it's not equal to that. I want you to say, well, the removable discontinuity is equal to that. It's equal to -8. Now you can cancel these out and then plug in x equals -8 into the simplified function. All right, so you're going to get -8 plus 1, and you're going to get -8 plus 4. So that's going to be -7 over -4, which is 7/4. And so this is your y value. This is your x value. And you're going to put them together. There is a removable discontinuity at -8, 7/4. It's also known as a hole in the graph, aka a hole in the graph. We call that a removable discontinuity. It makes a little more sense if you actually draw it all out. So let me just do a rough sketch of what this thing looks like. You'll see why we call it a hole. Excuse me. We call it a removable discontinuity because it's as if that point has been removed from the graph. It's like been plucked out of the graph. Let me summarize everything that's going on here. So this is our function, yeah? And then this is our factored function. And then we cancel the common factor, giving us a much simpler function, yeah? X plus 1 over x plus 4. So if we summarize all the details, summary of the details, the horizontal asymptote would be 1. Yeah, because these have the same degree. So it'd be 1 and 1. Yeah. The vertical asymptotes, well, it looks like there are 2 vertical asymptotes, but because of the removable discontinuity, that one has been removed. Yeah. And it's been replaced with a hole. So that means there's really only 1 vertical asymptote, and that's at -4. When you solve this denominator, setting it to 0. However, the domain, this is the one exception, the domain also excludes -8. Barely got that in there, but here, that's driving me crazy. I have to do that again. -infinity to -8, union -8 to -4, union -4 to infinity. So even though there's only 1 vertical asymptote, there are still 2 excluded values, -8 and -4. So this value is still excluded from the domain. All right. So let me try to give you an idea of how it looks on the graph here. I need to get all the way over to -8. So 1, 2, 3, -4, 5, 6, 7, -8. There is a vertical asymptote at -4. There's a horizontal asymptote at 1. Okay. I guess we could do a couple intercepts. Let's just mental math the intercepts. So the y-intercept, if you plug in 0, you get 1/4. 1 divided by 4, if you plug in 0. Or you get 8 divided by 32, if you use the original. Either way, it's still 1/4. So your y-intercept is going to be very close to 0, like that. Okay? And so this graph kind of looks like this. The x-intercept would be what? X-intercept, you just look at the numerator. Yeah, so numerator set to 0 be -1, so something like this. It looks like the reciprocal function's descendant. Yeah. And then you have another piece over here. So what is 7/4? 7/4 is, in your brain, you're thinking of 1 3/4. So right about here, there's a hole. And so the graph has a hole in it at -8 and 7/4. So 7/4 is just a little bit less than 2. It's 1 3/4. So there's your hole. And that's what we call a removable discontinuity. Okay, I guess I'm going to do one more of these. It's getting to be it's been about an hour already. I'll do one more of these removable discontinuities, and then we will move on. If they have no common factor, well, then that means there is no hole, no removable discontinuity. Let's see. I don't know. I haven't planned this one out very well, so I planned out my lesson, but I'm not sure what each problem is going to bring. I sometimes like to be surprised. So we get x squared minus 2x minus 48 over x squared plus 3x minus 40. And let's see. In fact, let's do the whole shebang here because I'm running out of time. Let's answer every question that we possibly can. All right? Everything that we've learned kind of in this one thing. So let's go for domain. Let's do that first. You might as well factor this out. Let's get started with the factoring. X, I'm looking at 40, so how about 5 and 8? If that doesn't work, I'll try 4 and 10. 5 and 8 work very nicely. If I make it a positive 8, a negative 5, boom, I get the 3 in the middle. All right, these are the relatively straightforward elementary algebra examples where the leading term is just 1. The leading coefficient is 1. 48, let's try 8 and 6. 8 and 6. All right. So it looks like we're going to get a removable discontinuity, but when we put in the signs, it's -8 and positive 6. So there is no common factor, so there's no hole. So the domain, -infinity to -8. Remember the opposite of this, because you're setting this equal to 0. I'm really kind of skipping steps here because we're getting towards the end. -8 to positive 5, and then from positive 5 to infinity. The VAs, you're going to get 2 of them. X equals -8 and X equals 5. Holes, DNE, because they have no common factor. Right? Summary of all of this stuff, the horizontal asymptote is 1. Yeah, 1 divided by 1, because these have the same degree. All right. X-intercepts. There are 2 of them. Look at the numerator. You're going to get 8 comma 0 and negative 6 comma 0. Those are your x-intercepts. And your y-intercept is, well, you have lots of choices. You can use the original, plug in 0, and you get 48 over 40. Yeah. Or you can use this version and plug in 0. Sorry, it's negative 48 over negative 40. You can use the factored version, and you'll get negative 8 times 6, and then positive 8 times 5. Yeah. So you're going to get 6/5. Yeah. The 8s are going to cancel. Yeah. And you'll get a negative sign, and then you'll have 6/5. But it'll be a negative divided by a negative, so it turns it into positive. Again, I just did that with mental math. Another way to do it, I like to just use the original. If you put 0 in for x to find the y-intercept, you put 0 in for x, and just reduce this. 48 divided by 40 is 6/5. Or you could think 1.2. Yeah. I like these little clouds. 6/5 is 1.2. Yeah. All right, so there are no holes in this one. It was close. Yeah, if it had those 8s been the same factor, identical factors, then there would have been a hole there. Okay, and then let's draw a graph, because there are some graphing problems at the end of this section. The graphing software is not that sophisticated yet. It's still kind of primitive. So it's multiple choice. So just draw a rough graph on paper and then try to make it look as nice as you can. I lost my pen. There it is. Ah, found it. All right. I kind of offset my thing here because I have to get all the way to 8. So 1, 2, 3, 4, 5, 6, 7, 8. There's my vertical. All right. Negative 6. 1, 2, 3, 4, 5, negative 6. Yeah, there's not going to be much graph on this side. All right, horizontal asymptote at 1. All right. My y-intercept is 1.2, so it's just a little bit above the asymptote. My x-intercepts, uh-oh. Do you see what I just did? I plotted the x-intercepts as asymptotes. These are the asymptotes. Oops. Well, I'm actually glad that happened, because that gives me a chance to rethink my graph a little bit here. Sometimes when I make a mistake, it's actually a good thing that that happened, because I can rethink how I lay out my board now. All right, the asymptotes. Let's start over again. Negative 8. 1, 2, 3, 4, 5, 6, 7. Negative 8. I'm going to drive you guys crazy, aren't I? Somebody's out there is going to get extra credit. Well, no, because I caught my mistake, so it's not eligible for extra credit. 1, 2, 3, 4, 5, 6, 7. Negative 8. There we go. Negative 8 asymptote. The horizontal was right. It was 1. Positive 5. So 1, 2, 3, 4. Positive 5. All right, I'm getting exhausted. It's been over an hour. You must be tired too. We're almost done. We'll just wrap this up. If you could do one of these graphs, you could do them all because they're all basically done the same way. So you draw your asymptotes first, you plot your intercepts. So I've got that one at 1.2. Again, I'm just approximating. I'm not being very precise. And then I got an intercept now at 8. So that gives me this piece. One dot really tells you the entire behavior in that area. And then -6, 1, 2, 3, 4, 5, -6. And so this is going to look like this. Kind of like a cubic. Yeah. And then it does have that familiar shape. So if one of the curves is in the lower right-hand region, then the other curve is in the opposite region. A lot like its ancestor, the reciprocal function. So had this curve been up here in that region, well, then this curve would have been down here in this region, vice versa. There's other behaviors like, for example, if the middle looks like a parabola, well, then these two end up in the similar regions, or sort of adjacent regions as opposed to opposite regions. So that's why it was important that this goes up like that. You could also plot some more points if you like. If you're not sure, it is multiple choice, so if you're consistently picking the wrong one, maybe just plot a few extra points. I'm not going to spend a lot more time on these graphs, mainly because this lesson's already gone on too long. I'm not going to film a part 3. I am available on Zoom if you have any questions or if you're having trouble choosing. For the part 1 graphs, I already gave you a demonstration on how to graph them using the software. But for these, just pick the one that looks the closest. There's not really a lot more that I can do because we're going to see each other. So I think we're done. I think I can call it a day. Again, this is Dr. Jordan. Until we meet again, I'll see you on the internet.